So this video is going to show you how to simulate inductors that are coupled together. Now this is actually doing the circuit that is in the EE3100 lesson 15 transformer example 1 video that you can find on my YouTube channel. And so I'm just going to go ahead and create the circuit here again. So I need some resistors. So I have a resistor here, another resistor, resistor, and a resistor. And then I also have a capacitor. And then I've got two inductors. And notice that when you place an inductor here, I'll put it over here, there is a dot here for the dot, so you have to make sure the dots are lined up in the same manner of the circuit that you are simulating. And actually I'm just going to flip-flop these because we usually have the primary coil being L1 and the secondary being L2. It doesn't really matter for simulation. And then of course we need a ground, so I'll put a ground in, and then we need a source. Now, you know, we just use the sine wave source here, but if you want to actually make sure it's a cosine wave, there is a way to do that. I'm sorry, you could actually do like a phase offset on these, but we're not going to really worry too much because it's just a phase difference. So the amplitude here is 300. I'm going to move it over a little bit. Frequency, well, it says it's 400 radians per second. So let me pull up a calculator here. 400 divided by 2 divided by oh, I'm like, why is it not letting me do decimals? Because I'm in programming mode there. I was using hexadecimal stuff. So let's see here, 400 divided by 2 divided by 3.14159, and so we get like 63.6 hertz. So I'm just going to go ahead and do 64 hertz, and then I'll just do the AC being 0. Alright, and so then we need to connect everything up. So I'll connect it up. Connect all of these up here. Ground there. And then let's change this here. This is 500. This is 200, so let me zoom in a tiny bit. This is 100. Again, this is 800. This is 1 microfarad. This was 4 henries. And this is 9 henries. Whoops, I'll just do 9 here. Now, 9. Now if I were to simulate this right now, it wouldn't do much here. But let's go ahead and set up a simulation profile here. So we're going to do transient again. And then knowing that the frequency is 63.6, as it's loading in there, I'm going to do the reciprocal of that to figure out the period. So we're at 0.015 or 0.016, so that's 16 milliseconds. And you know, let's maybe run for 10 periods, so 16 times 10 is 160 milliseconds. So let's do 160 milliseconds, and then let's start saving after 80 milliseconds so we can get rid of the transient response. And then we'll do a maximum step size of maybe 0.01. It might be too small, but we'll go ahead and try that. Milliseconds. Now, I haven't coupled these together. I want to show you what happens if you simulate it just as is. Now, the other thing I want to point out here is I'm going to see here. I think just lets me just draw a little bit. All I'm doing here is drawing some lines here. This has nothing to do with the actual circuit simulator. Okay, so it's all connected up. And I mean, you can change the properties of these and everything, but these are literally just lines that have been drawn around. And then I'm going to add some text here. And so I'm going to say transformer. And I'm going to literally just put it right here. So what this is basically saying is that inside this box is really the transformer. You know, I've got these internal resistances on the transformer, and that's just to remind me, because basically what I want to do is I want to measure the voltage from here all the way to ground. So to make sure that I'm going to be measuring that voltage properly, what I'm going to do is I'm just going to put a voltage right here, and it's going to measure that with respect to ground, and then that voltage probe right here with respect to ground. And I'm going to go ahead and simulate this. And as we wait, simulation, and look at this. We get a nice little 300 volt, essentially, sine wave, but look at the output. There's nothing there. If you zoom in, if we maybe delete the one, we might say, oh, there's something there. Let's look. No, it's flat. And the reason is because these inductors aren't coupled together. So there's literally nothing going through. On this right-hand side of the circuit, there is no voltage source, there is nothing going on. So these inductors haven't been coupled together. So that's the reason we're not getting any kind of output. So of course what we have to do to fix this and to be able to simulate transformers, of course, is to couple them together. And it's actually a fairly easy thing to do. And so you go to analog, and then there is something called K-linear, because these again are linear transformers. And you can even see it says coupling equals 1 here. So I'm going to put this in here and put K linear. And then of course we know the coupling coefficient for this problem was 0.5. And then what we need to do here is we actually need to edit a property here on this linear, because if I were to simulate it again right now, it's going to fail because of net listing errors, and it's because of this coupling capacitor, because you haven't told it anything that's coupled together. And so what we need to do is you go to this K1 and you go to edit properties. Now if you have it like this, it's kind of a little bit more difficult to read, so I like to pivot the table here. And then you actually have this L1. You can couple up to 6 inductors here. Now this is where you have to be careful. It's not that you need to have L1 there. What it is what inductors are coupled together, and you use the names here. So it's coincidence, and I'll show you in a second what I mean by that. This is L1 and L2. So I need to put in here, where did my property go here? Oh, because I went back to this, so there we go. I need to put in here L1, and then put in here L2. Now technically, actually, you could flip the order of this and it wouldn't matter. So I'm going to now close this. I've coupled those in together. I'll go ahead and save this as well. Now I can run my simulation. And you can see I now have an output with the red curve that's coming out of the transformer and a green curve here, which is the input to the transformer. And we can see that this is a step down transformer. Now we can also see what happens, like, okay, well, we've got that here. Let's just take a rough estimate here. So that's like, okay, like 1, what would that be? 2, 4, 6, 160 roughly as the output there. Well, let's go ahead and change this to 0.99, so essentially 1. Resimulate it, and you can see the voltage actually increases here because those are now stronger the inductors are coupled together stronger, which means that more of the voltage slash current is going to be transferred or stepped down or stepped up between them. Now if I do the exact thing and I, for instance, go down to 0.25, we can see that the voltage drops here. So the coefficient of coupling absolutely affects what the output voltage is. So I'll go back to 0.5, simulate it again, and we get this nice little output graph. Now if you were to also wanted to do current, I wouldn't try and do these all in the same graph, because okay, well the voltage are at the same units. Okay, so I would maybe, print this graph off, maybe do some computations, look at the frequency of the output, frequency of the input, they should be the same, what's the maximum output, maybe what's the phase difference between them, things like that. You could look at all those nice little interesting things and compute those and discuss about those. But then if you're going to also look at the currents, I would take off the voltages probes and then put the current probes on, so that I could look at the current and see what happens. Because otherwise, if you try and put the current and the voltage on in the same graph, well, let's just add one voltage probe here. Your current is going to be gone. You're not going to be able to see it. And that's because of you're in volts versus milli. Now there is another way. Instead of doing two graphs like this, you could also add a plot window here. So we've got here current plotted, and I've got this one selected now, and I could say add a trace, and I could remove the voltages and currents, and I could say, okay, well I want to add the voltage at resistor 1, actually it'd be resistor 2, terminal 1, and so it'd add that voltage there that's coming in, and then we could add another voltage, add trace, and I could look at the voltage on R3 on the opposite side of the pin 2, and we could see we get the voltages there. So there are ways to plot both the voltage and the current in a single graph like this, but you actually have to have two kind of subplots like this. And of course you could still do all the computations. The other thing I want to point out is SEL, that stands for selected. So if you were to do evaluate measurements, you'd be evaluating, or if you were to look at cursors, actually it's not the evaluation. If you were to look at cursors right now, if you were to add some cursors on here, I forget where is this, toggle the cursors, it's going to be on the selected plot as opposed to the one that's not selected. Alright, so I'm going to take those off. So that's just a quick example on how to couple inductors together. And again, these resistances are kind of the internal resistances.